Graphical misrepresentations of data. We want to be ethical statisticians. And so to be ethical, that means that you want to make sure that what information you're presenting is truthful and accurate. And so sometimes it's possible to misrepresent information by the way we construct a graph. And sometimes that can be done unintentionally, and sometimes that can be done intentionally. Regardless of whether it's intentional or unintentional, we want to be mindful of that and do our best to make sure that what we are presenting, the information that we are presenting, is accurate. Definition: the only science that enables different experts using the same figures to draw different conclusions. That's statistics. So this guy, that's how he defines statistics. The only science that enables different experts using the same figures to draw different conclusions. And there's truth to that definition. That's kind of a humorous definition, right? Not a real definition, but there is truth to that. Different experts can have different opinions about what figures might mean. But again, we want to be careful that the information we're presenting is accurate and not, at least particularly not intentionally misleading. So that's what this section's about. So example, a home security company located in Minneapolis, Minnesota develops a summer ad campaign with the slogan, quote, "When you leave for vacation, burglars leave for work." According to the city of Minneapolis, roughly 20% of home burglaries occur during the peak vacation months of July and August. The advertisement contains the graphic shown here to the right. Explain what's wrong with the graphic. So again, the point here is graphical misrepresentations of data. Now, this is an ad campaign whose purpose is to try to sell security systems, right? So they're wanting to present a picture of your house could be broken into when you're on vacation, so you should purchase a security system. But what's wrong with the graph? Well, the intent of the graph is to emphasize that in July and August, 20% of burglaries are occurring. So they show what's happening in July and August, and then they're showing what's happening in other months. So 20% of burglaries happen July and August, 8% occurs in other months. What's wrong with that? 20% and 8%, that's only 28% of burglaries. So how can that be? Well, I think probably in their zeal to show the disparity between July and August and the other months, they made an unfair comparison. So what they're doing is they're comparing a total of 20% for the months of July and August to an average of 8% for the other 10 months. So the 8% is actually 8% each of the other months, which would make up the other 80% of burglary. So 20% and 80%, that would make 100%. But even then, it's an unfair comparison because we're comparing a total to an average, and that's unfair. So we would be better off to at least, if we were to average and say, you know, if we took 20% for July and August and divide that by 2, that would be 10% in July and August on average versus 8% on average each of the other months. So that would show a 2% increase on average. That would at least be more of a fair comparison. So the sum of the percentages over all 12 months should be 1. Because 10 times 0.08 plus 0.20 equals 1, it's clear that the bar for other months represents an average percent for each month, while the bar for July and August represents the average percent for the months of July and August combined. So again, that's a total percentage on average compared to an average of the averages, which is unfair. The unsuspecting reader is misled into thinking that July and August each have a burglary rate of 20%. The new figure to the right gives a better picture of the burglary distribution. So this right here would be a more fair graph, a more accurate graph showing what's happening actually each month. So we can see that it does peak like in July, looks like around 11% of burglaries are occurring in July. But interestingly enough, only maybe around 9% is happening in August, which is actually less than what's happening in September and October. So this gives a more complete picture. So again, what's the point? We don't want to do these kinds of misrepresentations, right? We want our information, when we make it into a graph, we want it to represent what's actually occurring. So we want to be careful. Obviously, don't do this kind of thing on purpose, right? But even if it's not on purpose, it's bad. Another example, it's a different kind of scenario. A national news organization developed the graphic shown in the figure to illustrate the change in the highest marginal tax rate effective January 1st, 2018. Why might this graph be considered misleading? Well, take a look at this. So again, the graph is supposed to show what the highest marginal income tax rate is in 2017 versus 2018. So looking at the graph, in 2017, the highest marginal income tax rate would have been around maybe, looks like maybe 39.6 or 39.7%. In 2018, it had dropped to about 37%. So what's misleading about the graph? If you look at the graph, you can obtain accurate information. The trouble is, if you just look at a glance and you don't pay particularly close attention. So it was 39.5%, let's say, and it dropped to 37%. So that's a 2.5% decrease. But if you just look at the size of the bars, this bar looks like maybe somewhere between a third and a fourth of the size of this bar. So it makes it look like the cut to the highest marginal income tax rate was much greater than it really is. So that can be misleading. So the graph in the figure may lead the reader to believe that the marginal tax rates are almost 3 times as high in 2017 as in 2018, since the height of the bar for 2017 is almost 3 times the length of the bar in 2018, when in fact the difference is only 2.6 percentage points. The reason for this incorrect conclusion is due to the fact that the vertical scale does not begin at 0. So starting at 36 right here on the horizontal axis instead of 0, that can mislead, because if you look at the size of the graph, it will make the distinction seem bigger than what it actually is. A graph that does not distort the difference in the tax rates given in this figure, notice that the decrease in the tax rate is still apparent in the graph without the distortion about the size of the decrease. So again, you can see this bar for 2017, this for 2018. You can see there was a decrease, but the decrease doesn't look near as extreme. And this is a more accurate graph of what really happened. And we're starting at 0 instead of at 36. So the relative comparison is a fairer comparison. The time series graph to the right depicts the number of residents in the United States living in poverty. Why might this graph be considered misrepresentative? Now we have a couple of issues going on in this graph that we have to be careful about. The first thing is we have the same kind of issue that we had up here in the previous graph. We're starting here at 30,000, and incidentally, this data is in thousands. So when it says 30,000, that's really 30,000, which is 30 million. So 30 million, 35 million, 40 million, 45 million, 50 million. And this is the number of people living in poverty by year. So if you look at the bar and analyze the site, it looks like maybe 32 million individuals were living in poverty in the year 2000. And that increased to be more like 33 million in 2001, and so on. So we have the issue with the relative comparisons because this doesn't start at 0. That's one issue. But a bigger issue for this particular graph is that it is probably not making a fair comparison of the actual data. Here's what I mean by that. From 2000 to 2017, the population of the United States has grown. There's more people in the United States in 2017 than there was in 2000. So comparing the raw numbers is probably not the most fair way to make that comparison. So instead of looking at the raw numbers of individuals living in poverty, maybe a fairer comparison would be to look at the proportion of individuals living in poverty. So the graph may mislead readers to believe that the number in poverty has more than doubled from 2007 to 2014 because the bar of 2014 is more than twice the length of the bar from 2007. Notice that the vertical axis begins at 30,000 instead of 0. This type of scaling is common when the smallest observed data value is rather large number. It is not necessarily done intentionally to confuse or mislead the reader. Often the main purpose in the graph, particularly in time series graphs, is to discover a trend rather than the actual differences of the data. So again, the author points out that one issue is not starting at 0, but to be totally honest, that is somewhat commonly done on time series graph, because usually a time series graph, the intent is to look for a trend. It is better to use a time series plot when displaying time series data rather than a bar plot. In addition, it is better to use the percent of the population in poverty rather than the number living in poverty. This is due to the fact that increases in poverty may be due to increases in the population as well as deterioration of the economy. So again, if we look at percentages, that's going to give us a more accurate indicator, particularly if we're talking about things like economics. A bigger population is going to automatically result in a higher frequency. So relative frequency is probably a better thing to look at. So here the data have been converted to percents. And so we're using a time series plot like a line rather than bar graphs. And we've indicated here that we've changed our scale, which means it's okay to look at the trend, but don't look at the relative size. So in 2000, a little over 11% of the population was in poverty. It increased in 2001, 2002, 2003, 2004. So the percentages went up, but in 2005, the percentage actually went down a little bit, same in 2006, then back up and so on, which that's not as obvious in the bar graph, how much that went down that we were seeing up here. Then it went back up, and it actually went back up at a relatively stark amount, and then it actually decreased again, back up, and then decreased again. Anyway, the point is, it's a better comparison to look at the proportions and to do that using a time series plot than a bar graph. So again, just be mindful of those kinds of issues. Next example. The bar graph illustrated in the figure to the right here is a USA Today type graph. A survey was conducted by Impulse Research for Quilted Northern Confidential, in which individuals were asked how they would flush a toilet when the facilities are not sanitary. What's wrong with the graphic? So this is a graphic. It's kind of clever. We're talking about how would you flush a public toilet. And so we have three possibilities: use shoe, act normally, use a paper towel. Now this is relatively old. This was prior to automatic flushing toilets being almost everywhere now and that kind of thing. So if you had to actually flush it, how would you do that if it wasn't particularly clean? So what's wrong with this graph? It's clever, it's eye-catching. So like if this was in USA Today, the newspaper, for example, the purpose would be it's trying to grab people's eye, to really a somewhat trivial thought. So what's wrong with it? Well, if you look at the heights of the bars, so to speak, and again, it's clever. I give them a A+ for cleverness, using like the roll of toilet paper, you know, as the bars on a histogram. That's clever. But if you look at the relative size, 41%, 30%, 17%, is that going from here to here? Is that supposed to be 41% and that 30% and that 17%? If that's the case, the relative size doesn't match up. But maybe the horizontal axis is supposed to be at the top of the roll of the toilet paper. That's unclear. Another issue that a lot of times students tell me is an issue with this problem is that if you add up 41%, 30%, and 17%, that only adds up to 88%. That's not 100%. In this particular case, I wouldn't really consider that to be a huge problem because I would assume that the other 12% were other options. So I would assume there were other things that people stated and they just didn't make a bar for everything. So again, the issue is that in the cutesiness of the graph, we lost the scale. Another example, this is done all the time. It is never, ever a good idea to try to use the comparison of the sizes of two objects to try to make a statement about how something has changed. It's almost always misleading. So soccer seems to be losing popularity as a sport in the United States. In 2010, there were approximately 14 million participants in the United States. By 2014, this number had dropped to 12 million. To illustrate this decrease, we could create a graphic like the one shown in the figure to the right. I said below, but to the right. Describe how the graph shown may be misleading. And this information comes from the US Census Bureau. So again, this ball is supposed to represent how many people were playing soccer in the year 2010 versus this ball supposed to be showing how many people were participating in soccer in the year 2017. This is supposed to be representing 14 million people. This is supposed to be representing 12 million people. Do you get the 14 million and the 12 million from that? It doesn't work, right? It doesn't work. The smaller ball does indicate that soccer participation's gone down, but if I looked at the size of these balls, it would seem to me that this indicates it's gone down a whole lot more than it actually has. So the size here is supposed to be illustrating a drop of 2 million participants. Doesn't really jive. The size doesn't match that figure. So a better thing to do is definitely never use size comparisons such as this. But if you want to use a cute graph, you could do something more like this. This is called a pictograph. So if each soccer ball represents 1 million participants, then in 2010, we have 14 soccer balls for 14 million participants. In 2017, we have 12 soccer balls for 12 million participants. And so we can clearly see the difference is 2 million participants. So we can have cute graphs without having misleading or misrepresentative graphs. The last topic here that we should generally avoid is three-dimensional graphs. Three-dimensional graphs look cool, but they're almost always misrepresentative of information. So take a look at this three-dimensional circle graph. The figure to the right represents the educational attainment in 2017 of adults 25 years and older who are US residents. Now, this is the same data that we used back in section 1. We were looking at levels of education. This graph is pretty cool looking, a three-dimensional pie graph. The trouble is to create the perspective so that we get 3 dimensions, the graph overemphasizes the categories that are in front and de-emphasizes the categories that are in back. In other words, relatively, when you look at this, it looks like the pieces in the front are bigger than they actually are. And it makes the pieces that are in the back look smaller than they actually are. So again, this is that same data that we used back in section 2.1. Now, If I take this same data, the same data, which incidentally I've included right here, and if I just rotate the graph, take a look at these two. I'm going to put them side by side here. So we have not a high school graduate right here in front, and we have some college, no degree in the back here. Now, all I've done is rotated the graph so that some college, no degree is now in front, and not a high school graduate is here in the back. It's the same data, I just rotated it. Do you see what happens to the graph? Here, that looked like insignificant almost, right? Now it looks like, ooh, that's a big deal. Same deal. This looked like a big deal. Now it's kind of back here. This, I should say, now it's kind of back here. It doesn't look all that significant. So that's the kind of thing that happens with three-dimensional graphs. And so you could end up misleading someone who's looking at your graph just because what's in front. A better thing to do would be just to create a plain old two-dimensional circle graph like we have here, and then we don't have the distortion. So some guidelines to construct good graphs. Title and label the graphic axes clearly, providing explanations if needed, include units of measurement and a data source when appropriate. So if you're creating a graph, it's always a good idea. Make sure you've labeled everything very clearly. If you can't label it clearly enough, provide a written explanation that goes with your graph. And then put a source where you got your data so that if someone wants to study it more, they can go to the data. Avoid distortion. Never lie about the data, right? That's unethical, and we want to be ethical. More and more, that's becoming a problem. Marketing, companies want to sell, and so they will distort things to make it look like you need their product more than maybe you actually do. Politicians distort things so that they can achieve their agenda. And so more and more that's becoming a problem. And so we want to make sure that we have integrity and that we don't distort. Minimize the amount of white space in the graph. Use the available space to let the data stand out. If you truncate the scales, clearly indicate this to the reader. So truncating the scales, we saw that like here, right? So this was truncated. We changed the scale, so that little mark right there indicates that we've done that. So again, that's a message to pay attention maybe to the trend more than the actual values. Avoid clutter, such as excessive grid lines and unnecessary backgrounds or pictures. Don't distract the reader. Avoid three dimensions. Three-dimensional charts may look nice, but they distract the reader and often lead to misinterpretation of the graphic. Do not use more than one design in the same graphic. Sometimes graphs use a different design in one portion of the graph to draw attention to that area. Don't try to force the reader to any specific part of the graph. Let the data speak for themselves. And then last but not least, avoid relative graphs that are devoid of data or scales. Again, don't use relative size comparisons. That's always misleading. Never a good practice.